systems with a small amount of I&I, but still, if it's limited capacity, some part of the system may still wind up having SSOs and backups. But one thing that seems to be a common factor in all of these different ways that I've categorized it, whether you have a system with excess capacity or low I&I or whatever, is the fact of having deterioration of pipes due to the movement of soil fines. Now, what this translates as is I&I and deterioration of systems does not improve on its own. If let go, it will continue to deteriorate the systems. Another point is I feel like the best time to address this long-term problem is during the actual planning and the engineering of any kind of sewer rehabilitation work. That's whether you use grouting or other means to stabilize the soil and isolate the groundwater movement. And certainly what Corey was talking about in the introduction would be one means of accomplishing that. Now, another point that I think is, to me, a kind of a given, but when I have conversations with various people around the country, there's really a question in their minds whether an I&I can be reduced, which is often the reason why they turn to expanding the plant or building tanks or trying to upsize facilities. And the answer is resoundingly yes, I&I can be reduced. In fact, in earlier research that I've published, that I've seen that 50% reduction is a very realistic target. Now, I've seen a lot of projects and have been involved with projects where much more than 50% has been reduced, but I think this starts getting us into the realm of when it's really worthwhile talking about doing sewer rehabilitation to accomplish I&I reduction. The cost for doing reductions, and again, I'll be documenting this or explaining this further, but just to let you know what's going on, is a bit over $1 billion, I estimate, to accomplish 50% reduction across all 227 cities or 227 sewage collection systems in Tennessee, which are on a state permit system. The really neat thing about it is that if you think about the cost to accomplish this work, but you also look at the decreased cost of O&M, this can result in a payoff in about 10 to 13 years of actually the projects will pay for themselves in cost savings. Now, where this kind of the root of this research began in my mind was I've worked for the state of Tennessee, actually my first job. I've worked in a regulatory position when I was with the city of Chattanooga as system engineer, and I was constantly working with all the data and reports that had to be given to the state and to EPA. And it's when I'm showing it here as huge stacks of paper, well, guess what? Even in the electronic age, it still is huge stacks of paper. And I began to wonder, although we're using this information primarily to monitor compliance of how well people were meeting their permit criteria, I began to think, isn't there some way that we can use all this data to try to measure I&I? And once I thought about that, I thought, well, then if we could actually measure an I&I, would this be able to help improve our state and ultimately even our national control strategy for I&I? And personally, this is strictly a personal opinion, I don't think we really have a good state or national control strategy for I&I. It seems like that it's mostly just being very reactive and build bigger is better. Looking at the study then that evolved out of that, the first phase of it was I started looking at the DMRs. Now, some of you may more think about these reports as being the MPDS reports or the EPA monthly reports, but these are essentially the compilations of monthly information that's sent by every licensed municipal system to their state and or directly to EPA. And fortunately, now these kinds of reports have been recorded electronically, and they're actually available on EPA's website. But I began running into problems with these reports because using monthly averages means I was losing the picture of the peaks and valleys for a given month, which sometimes is very important. So I started looking at a second phase where I used the municipal MORs, the monthly operating reports. These are reports, actually the original reports that are where information is recorded each day individually, and then the information is averaged, and then that's what's converted then into the EPA report. In Tennessee, we have 227 systems that are submitting MORs. For my work, I've completed 187 of them, and that's looking at 12 months for each one of these systems. I began this in 2013. It's been quite a task because it's all in paper copies at this time. I have to transcribe it into Excel sheets. I've used 3 different methods. One is first to compare the 7-day low flow for each year that I look at to the annual average. This is very close to the method that is used by most practitioners, and is also one that's been most recently updated by EPA. But I've also developed a technique to look at the BOD dilution. BOD is a measure of the organic strength of sewage. And what it turns out for domestic waste, we all, to put it bluntly, kind of put out about the same amount. And I've found that the reason why there's a lot of variation in BOD concentrations coming into sewage treatment plants is that the variation is caused by dilution of various levels of I&I. And then finally, I look at the peak day RDII, the rainfall-derived I&I, and estimating that by regression techniques. This is very important because it's the peak day flows that are caused by I&I. They're going to cause violations, it cause the SSOs, cause plant bypasses if they're going to occur. So looking at the purposes of the study, I had several ideas in mind. One was, first of all, I wanted to have actual I&I data to give to policymakers, and I have to say that I'm hoping that this will stimulate a new statewide I&I control strategy. I think those of you who have been involved in research before, you know that just giving people data doesn't automatically result in new actions. I want to demonstrate simple, inexpensive techniques to calculate this because I think many people are daunted by being confronted with high caliber hydraulic programs on the computer. This is something that does not require a PhD. It is not rocket science. I'm not a PhD, and I'm not a rocket scientist. I can do it. I want to show the value of existing data sources so that people are not daunted by saying, well, we don't have the money to get into this because we don't have the money to be able to hire an engineer or to install new flow monitoring or anything like that. I'm showing that people have the resources right now to get at this. I'm using BOD, biochemical oxygen demand dilution, as an I&I indicator. I've never seen this done before. And also, I have an operations background, and so I wanted to develop a spreadsheet tool that operators at treatment plants could use to calculate their own I&I. But having said all that, I want to emphasize that this study itself does not replace a full engineering analysis for actually planning a program at an individual community, but it's trying to help people get a feel initially where they're at with their overall problem. Now, when I'm talking about the public resources, I've defined a little bit about what the 2 kinds of reports are. This is just to back that up, the DMRs and the state MORs. But the key point is all of this is existing data. The operators at treatment plants collect this daily. Going back again to phase 1 of the DMRs, when I did that, you know, as I mentioned earlier, I had 227 systems. Well, when I look at the EPA reports, they have a different way of defining public systems. So they had listed 235, but the basic reports are still coming out about the same. In doing that, though, I noticed that it seemed like I was missing a lot of I&I. The annual I&I was getting for using that data set was only about 25% of the influent, which is still quite significant, but I knew from my own experience of looking at monthly reports that it was a low number. But another thing that jumped out big time at me was this extremely wide range of influent BOD concentrations. That's the concentration of the organics actually coming into the treatment plant, going all the way from 3 to almost 900 milligrams per liter. This is there is no good way to explain that other than a high degree of variation with BOD, and also maybe some questions about operator capability of actually running the BOD test. But now let's look at what, if it's that kind of variation range, what really ought it to be? In other words, what is the concentration of BOD coming out of a house? And that would be the combination of the toilets, the sinks, the tubs, whatever, all kind of coming together. And a lot of research has been done on this, and I want to give full credit to this individual, T.R. Bounds, which he published an article back in 1997, and they found this kind of range, which actually measuring at individual households or groups of households before opportunity for dilution. And the EPA also looked at this, and they have published various guidance documents which recommended using 350 milligrams per liter as a concentration, at least a starting point concentration. Now, when I looked at the, or where I am right now at about 82% of looking at all the systems in Tennessee, and I've plotted out the concentration of BOD that I'm seeing, and this is the average concentration. Actually, the low level is much lower than this, but you can see where the point of 350 comes in is right about here. Well, there's only about 10% of all the systems that I've looked at that are greater than 350. Well, what does that mean? It means that in this case, about 52% have greater than a 2-to-1 dilution, and principally that's by the leakage coming into their system. So they're treating a very dilute waste. And again, emphasizing the point that most BOD variation, from my experience, results from ionized dilution. There are a few exceptions to that, maybe from certain kinds of industrial waste. Now, I've talked about MORs, and this is actually a typical MOR report. You can see each day is listed here. And then the values that are shown in red, those are the kinds of values that I'm collecting. I'm looking at rainfall. I'm looking at influent BOD. That's the incoming flow into the treatment plant. And then I'm looking at the influent BOD concentration, in this case 79. That tells me this is very, very dilute. There's, and all this has, so far I've transcribed about 103,000 data entries to get this into Excel sheets where I can really process it. But it also shows some other problems that I think occur with these reports. For one thing, people aren't measuring BOD every day, and this in some cases is a problem with the permit limits that are established by the state. Another thing, they're not filling the thing out completely, and we're looking at the max flow, which would give me a little bit better idea of what's going on. But anyway, setting those problems aside, this is what the final, or the initial electronic step looks like. Once all the data has been transcribed, then I can generate a hydrograph. The hydrograph is the black line here. That's the graph of the flow, just the daily flows. And then the blue lines, the bars here, are the hyetograph, which represents the daily rainfall quantity. So the rainfall is on the right side, the influent flow is on the left. So I mentioned earlier that one of the methods of trying to define ionized is to calculate it using the flow values and also rainfall events. And we're making an assumption here that the main sources of variation are seasonal. Going back just a second here, you can see more in the early spring, we're having high flows. It's starting to come up again. Now, we did have some really exceptional rainfall events in the middle of the summer that popped it up. But generally, it's seasonal, and then you can see how the peaks are related to the actual rainfall events. So that we're having the seasonal effects and then the rainfall events. So if this assumption is true, or this set of assumptions is true, then any flow greater than the dry weather, dry season, is due to I&I. It also makes the assumption that the dry weather, dry season flow is solely from users. Now, I put this in italics because we're going to see an example later on where that may be questionable. But anyway, going back to our example here, and by the way, I use the city of Bristol, Tennessee. I didn't have it in for Bristol. There's nothing they particularly were doing bad or good, but the reason I used Bristol was actually they had very good data on their BOD levels, and so I had a high level of confidence that they had high quality data, and it also illustrated some of the points I wanted to use here. So in this case, the gross annual average on a daily basis for their flow of coming into the Bristol plant was 9.8 million gallons a day. When I go through all the day's flows and do a sliding 7-day average, it turned out that this period right in here is the 7-day average low flow, and that was 6.63 million gallons a day. So what that remains then is that the hashed lines here underneath above the red line, which represents the low flow, but is also under the actual hydrograph, that means I have a gross average of wet weather and wet related events of I&I of 3.2 million gallons a day. So that represents like about a third of the total flow, which would be significant enough. But it also had some questions that I'll get into here. Just showing the calculations for the example for Bristol, it works out to be a little over, well, about 1.1 billion gallons of clear water coming into that plant in a year. But the problem is that when I looked at this 6.63 MGD as being the low flow average, that was still much greater than what I would have expected from the overall population of Bristol, which was about 50,000 people. And so this raised some questions. And the question is, does that number of 6.63 MGD as low flow really, is that only the population, or does that perhaps include some significant infiltration of dry weather infiltration? So I started looking at a different technique to get at that. And I said, and essentially I'm looking at the dilution of the organic waste coming into the plant, or as being contributed by the customers in the system. So the question is, what is the quantity of flow without I&I? And to do that, again, I referred back to the work by bounds, only I decided to be even more conservative, that rather than using 350, I'd use 300. And I use this to improve the estimate of the base flow. And I did this by calculating the daily amount of I&I that it would take to dilute the full strength BOD, I'm assuming at 300, to dilute that down to the actual concentration which was measured in the influent. I did this for each individual day. You can't do it on a gross average. And in this particular case, for Bristol, what it turned out was that the total, using just the dilution, the total amount of I&I, which would be the wet I&I that you already saw, plus the dry weather infiltration, was about 5.9, close to 5.9 MGD. So when I subtracted off what I already had looked at for the wet weather I&I, that gave me a dry weather infiltration of 2.7. This is going on continuously. So again, going back to our chart, now we have a much better understanding. We still have the wet weather I&I, or wet season and wet event I&I of 3.2. But now we know that there's also an ongoing continuous dry weather infiltration of 2.7. And then finally, we have a mass population base of actually contributing from people of about 3.9 MGD. Now, the dry infiltration might raise a question, well, where's that coming from? Well, you can have that particularly up in East Tennessee, where you have a lot of rugged terrain, and if you have pipes laid down near creek beds that are running continuously, if you have leaks in those pipes or leaky joints in those pipes or cracks, then that saturated groundwater could be coming in on a continuous basis. So now we're starting to look at the results from the whole study. And we see that we have Bristol plotted here, and actually what it had is about 59% of its flow on an annual basis is clear water. It's I&I. And I've plotted it against all the other, it's kind of at a midpoint practically, with all the other cities I've done so far, all the 187. And on a gross average basis, now this is actually looking at the total amount of I&I. This is not the average, the midpoint here in this chart, but the total amount of I&I versus the total amount of flow coming into all the plants that I've looked at is about 44.5%. So this is a really significant amount to be dealing with. So, okay, that seems to be good for looking at annual I&I, but what about the peak I&I? And the thing is, this is important to look at because it's the peak levels of peak day flow which is going to cause SSOs or cause plant bypasses. And then I developed a transformation procedure to handle the data. This kind of data has actually been looked at for years. I've found old reports where people would try to plot the influent flow on a given day against the rainfall. But the trouble is when they would do that, they weren't accounting for the fact that there's usually a delay in the time when the peak flow would hit the plant versus when the rainfall would happen out in the system. So I developed a set of transformation procedures, and these were published back in 2009, and you'll be getting, or you'll have the opportunity to get a longer list of these references, so you don't have to worry about writing them down right now. But I just want you to know where this stuff came from. But when I worked out this transformation procedure, it resulted in getting a 3 to 4 multiplier on the improvement in the regression correlation, which I always like to look at the statistical quality controls for any kind of analysis that I'm doing. And plus, I also had some tests where I compared the results for an identical result with, or identical data where I had hourly flow data, and I was able to get within about 12% of that projected peak. So I felt like I had a lot of confidence with that. Just briefly touching on how this works is you see here the original data that I would have pulled off from the MOR information, and this is the format that it would come, and I boiled it down onto the Excel spreadsheet. And I give the rules here that by looking at the the total of the rain over 2 days, and then looking at the second day RDII, that what I would then select is this would be the data set that I would be plotting. And to show you an ultimate result for that, again, going back to our data from Bristol, this is a plot using wet season information. Now, you saw earlier that there were some heavy events which were occurred in the summer, but these events are not really going to be valid because they're not with saturated ground. Now, I mentioned about using statistical techniques. I took the same data, again, plotted out the regression, and also plotted out the 95% confidence interval. And you see this has a pretty darn good confidence interval of 31%. That's very, very reliable. And also, just kind of a reference point, because I'm going to be coming back to this later, is the 2-year storm. It shows that a 2-year storm of 3.4 inches will cause the peak day, or the 2-day rain I&I, to far exceed this level here, which represents the remaining plant capacity to handle any I&I. So once I had that kind of data for each of the 187 sites I've looked at so far, you can see here that Bristol's showing up, is that it's showing that 83% of the systems I've looked at so far exceed the plant capacity for whenever a 2-year storm occurs. In fact, many of them, most of them, exceed their plant capacity for storms which are much less than that 3.4 inch. See, the 3.4 inch is right here, but this might be for a 2-inch storm. So that's showing all these would exceed for a 2-inch storm. When I actually looked at the data of what people reported that they exceeded, it was paralleling that previous curve. And additionally, it showed that 27% of the plants had days when they exceeded the plant capacity more than 60 days in a year. So let's look a little bit at cost, because everybody's interested in their wallet, and also look at the sewer rehabilitation and payback. And taking the numbers that I've already mentioned about the total amount of I&I that we measured here in Tennessee, or that I'm in the process of measuring, again, the 111 billion gallons a year, The annual cost using an O&M cost of $1.80 per 1,000 gallons works up to be about $200 million a year. That's basically $200 million a year just getting thrown down the drain. It's not doing any good whatsoever, except it's just a pass-through at the treatment plant. Now, assuming then a 50% reduction, the math is real easy. If we cut the $200 million a year in half, then we get a savings of $100 million a year. Now, the trouble is trying to tie that in. What's it going to cost for us to do rehabilitation to achieve that 50% reduction? And to do that, I've turned to a graph that I developed a number of years ago, and again, there's a reference for this in the PDF. I went back to work that was done in Nashville, and it includes about 130 miles of lining, which was the largest amount of data, at least that has been published publicly. There are certainly programs with larger amounts of sewer rehabilitation that's been conducted, but to the best of my knowledge, this is the largest project that's been published with all the details involved. And for Nashville, there was like about 27 different project areas, and for Brentwood, there's like 6. So when I plotted them out, I got a relationship between the amount of rehabilitation work that was conducted and the amount of annual I&I that was accomplished. I would emphasize that this was relying on, or one of the conditions is using a system approach where that includes rehabilitation of pipes, laterals, and manholes, and keeping in mind what we talked about earlier of stopping migration of getting into the pipes and laterals and manholes. We've got to stop all the migration to any of these points, which of course will include stopping flow in the soil around the pipes as well. We've got to stop that entry. But using that information, then I come up with this factor here of 0.006 million gallons per foot of reduction. So applying that to the total amount of reduction that we want to achieve that we had on a previous slide, and then of course converting to miles, what that boils down to is about over 1,700 miles of rehab. That's end-to-end lining that would have to be conducted, as well as the included manholes and laterals. When we look at the cost there, and again, this cost of $0.6 million per mile, that came from work again that was done in Nashville. It's obviously a very gross average type of figure because it would include different kinds of pipe at different sizes of pipe, usually in the size range of 8, 10, 12, maybe even up to 15 inch. If you have a lot of large pipe, it's going to shift the number a bit. But what it boils down to is that comes up to a total cost of a little over $1 billion. Well, now we get into really some complicated math. If you take that $1 billion and you divide it by $100 million of O&M savings a year, what you get is a payback period of between 10 to 11 years. So, in recapping some of the principles here in order to accomplish that, and again, these are in some more of the reference documents. One is a focus on priority basins, rehabbing the pipes, manholes, and laterals, halting the migration, halt the migration and the tracking inside the pipe, namely the part that's in the annular space between the new liner and the old pipe. This is often by providing seals at the manhole junction, renewing the service laterals, and a key point is verifying the results by monitoring, both before and after. In my mind, the project is not complete until the monitoring verifies the actual reduction. I'm going to briefly touch on the Brentwood rehabilitation. This is a fairly small system, but it's actually the size still of many communities here in Tennessee. They have about 155 miles of pipe, 4,000 miles of 4,000 manholes. We relined about 21% of that system. Also sealed and lined about 1,400 manholes, and they're in the process of doing more laterals, but at the time that the study was done, they had about 320 laterals completed. The results were they knocked out, and we documented before and after monitoring, 886 million gallons of I&I per year. That's over 50%. And they're actually monitoring the savings of $1.3 million a year because they've got a meter where they pay Nashville to handle their wastewater for the actual treatment process. This graph shows how we actually, or one of the tools that we use for monitoring the decline of I&I in the system. And you notice there's a couple bumps here. This one is a big one. Well, it turns out that it had a big, significant drop here. And the reason for that is the 2010 flood that was took care of the whole Nashville area, and there was suddenly 12 inches of rain that fell in 2 days. And because of the math in calculating the annual I&I number, that resulted in this drop. After a year, since this is a running average, after a year it popped back up. So I'm going to show that as really just kind of bridging over there. But there's another bump here that's rather disconcerting. And it turned out, we found out over a period of time that there was a 750,000 gallon a day leak that had suddenly opened up right next to the Little Harpeth River. And we repaired that leak here in December of 2013, and then now you see that it's dropped back. So really, if we hadn't had that leak occur, you'd see this would be quite a continuous downward trend, and it does in fact represent the amount of reduction that we plan. In conclusion, just looking at some points that I felt for management needs to be concerned for I&I reduction. First of all, I think it's very important that we have a paradigm shift. We need a paradigm shift with the regulators, but we also probably need some paradigm shifts within the communities to be looking at doing monitoring to go a step beyond compliance monitoring. We need to be looking how we can use this information to help plan our programs. This is probably another way of saying we really need to implement life cycle analysis. Instead of just responding with a knee-jerk reaction to build new plants and build big tanks, we need to look at the long-term costs of actually getting at the root problem. Electronic records. After I've worn my fingers to the bone, boy, I'm certainly I'm strongly in favor of electronic records. It can't be overstated. I think this has been a huge hindrance of having the paper records that people have just ignored looking at the data. Operator training. I think there needs to be more training on doing BOD analysis and on doing sampling. I think the governmental agencies need to be more proactive with guidance on rehabilitation programs. And finally, probably just the overall topic of public education is really going to be important. I want to give a quick acknowledgement to the Division of Water Resources in Tennessee. They've helped me gather the reports. People have been very cooperative, the individuals at the various basin offices. Also, some of you probably recognize the cartoon illustrations. These came from the EPA Sacramento State course. I figure that we're all taxpayers, and I paid for part of that, so I feel like as long as I give acknowledgement, I can use them. Certainly want to recognize good work that was done by the City of Brentwood and also one of my former companies, Barge, Wagner, Sumner, and Cannon, which had the program assistance contract for that work. Finally, let's go ahead and get into questions. And again, I want to point out that the narrative results will be available with a list of references after the webinar.
Okay.
What do I need to do here?
Thanks, George. Yeah, I'll go ahead and jump into it. And this is kind of a voice of the dark. This is Robert Armstead with Eurotech Holdings, and we've got a few questions. A quick note, if you look in the toolbar for your webinar window, you can see an area called questions. I'm going to open up that section, and if you want to submit a question, please do so there. All questions are welcome, and I'd love to hear your input. So I'm going to jump into it. How do these numbers factor in some sewer systems that have already been rehabilitated, i.e. some plants, services, both rehabbed and non-rehab basins?
Well, that's a good question. And essentially what I've done, this study is truly just a snapshot. Some of the systems have in fact conducted rehabilitation, some have not, and then like you say, usually what the situation is that maybe they've conducted some rehab in maybe their worst basin, whatever they identified as being a problem. And I have no way to be able to determine what's going on in that regard. That is definitely a weakness of the study. And that's also why I brought up, or tried to make the point earlier, that this is to kind of give a 36,000-foot overview for regulators. Although I do have the individual studies for each individual town, and they can look at it and make their own judgments about it. But if anybody is planning to do launch a rehabilitation program or launch a new phase of a rehab program in a given town, they need to be breaking their system up into various basins and conducting flow monitoring and SSES work out in those individual basins. So there's a lot of things this study can do, but there are definitely limitations.
Okay. When you refer to laterals, does this include service lines?
Oh yes, I'm sorry. There's a number of different words that are used for that, and it kind of varies across the country and with different people. And that is exactly it. It's the service lateral. I'm generally thinking, when I say service lateral, I'm generally thinking about the point from the piping that is from the point of connection to the public sewer in the street or in the easement, all the way back to the point where it ties into the house or even under the house. That would be the complete lateral. Now, there's a lot of issues about what's the public part of that, what's the private part, who has responsibility, and that varies all over the country. WEF has done a lot of study on that, but for just talking about where the problems occur, it's anywhere in that system, and it certainly starts with the connection to the public sewer.
Great. What are the municipalities doing to ensure that new sewer laterals and manholes are installed properly to prevent future I&I?
Some are being very proactive about it, and of course, inspection is always, you can have the best design for a connection, but unless it's inspected and vigorously and critically, you can get just about any kind of garbage installed. But I think cities are realizing that this is part of the problem, and they are improving. Now, some of the smaller towns, they just simply don't, or at least they feel like they don't have the resources to have inspectors. But the reality is that it's pay me now or pay me later. If they don't make sure that this stuff is put in right, or they allow break-in connections, then they're going to wind up with I&I in the future. And that's really a tragedy, that we've got enough problems fixing the stuff we have now, but I'm horrified to think of that we're still building these kinds of problems into our system.
Hey, does your research give you any indication of how much of any particular treatment plant's inflow is due to normal industrial operations? Industrial operations generally will not follow the residential BOD numbers, and for instance, a stormwater oil/water separator as required by a facility's SPCC plan is inherently going to discharge more on storm days, and these frequently discharge directly to the POTW, which would yield natural non-I&I storm flow to the treatment plant.
That's exactly right, and that is another Achilles heel of this process, where I'm only looking at it right at the treatment plant influent. Now, sometimes I can actually tell I have a pretty good idea that it's some kind of industrial process that's going on, since I'm looking at both the variation in flow, but I'm looking also at the variation in BOD. But be honest with you, what I've had to do in order to get a really good fix on that is going back now to the state of Tennessee records, which are online, and I've reviewed each permit individually, and they usually will give an indication in there of the percentage of industrial flow that they are treating. So that gives me kind of an alert as to if I'm going to run into that kind of problem. But the honest answer is that there are some cities, I'll give you an extreme example like Memphis, which it's not so much a problem of I&I variation, but they have a highly concentrated waste such that their normal waste coming in the treatment plant is about 900 milligrams per liter. Well, it's because of the dump from Schlitz Brewery, which I'm very happy that they have a beer brewery there, but it has a high organic level coming in. So I can't measure what's going on with I&I in Memphis, for example.
Okay. So with this question, I'm not sure if it relates to an acronym, so please help me out. But it says, how did your dry flows estimated from BOD compare to 100 GPD using 10 state, and it says STDS, I'm assuming standards, but I'm not sure if that's and then question, and then did you get about 50 or 60 GPD, and that's in commas, 2.7 MGD over 50,000 population?
Okay. What I've gone back and done some separate looks at, I haven't reported everything in this slideshow because of just the length, but I'm seeing a rule of thumb kind of emerge, for my purposes anyway, of in towns without industries where I can pretty well allocate it out to the loading, that my rule of thumb for per capita discharge is about 68 gallons per day per person.
Okay, next question is, how much I&I have you seen from new, less than 5-year-old sewer collection systems?
I don't have a way to know because I don't have any information about the actual age of the systems. But I do want to comment about relying too much on age of systems to determine whether or not you potentially have a problem. I recently attended a seminar in October with regard to work that's being done in Fort Worth, and they were doing a study of remaining life of their large diameter sewers. And they came up with a rather startling conclusion from their actual inspections and correlating it with the age of the sewer, that they, in some cases, depending on the types of discharges or maybe the conditions of flow, which might lead to hydrogen sulfide deterioration, that sometimes they had very recent sewers which were deteriorating more quickly than sewers which have been in the ground for a much longer period of time. I have to admit, I still generally would look at older sewers with wanting to look at them more critically, but I just want to caution people that age is not an automatic indicator of either that everything's fine or everything's going to be a disaster.
Okay, it is noon at the moment. Let Corey take over just for a moment. The one note I will make is that we do have quite a few more questions that we'll go over, but go ahead, Corey. Corey.
Great, thank you. Thank you very much, George. That was very enlightening, and it's neat to see everything you've been doing over the last few years. So thanks for sharing that with all of us. As mentioned, this webinar is over, so anyone who does need to get back to their day, thank you so much for joining us. Greatly appreciate it. Our next webinar will be March 18th at 11 a.m. Eastern, and we've got a few different projects that we have the actual customers, whether they work for a municipality or an engineer, they are going to basically share their project with us and on the webinar why they chose us and maybe any benefits or cost savings that they've seen since. We shared that example of Clarksville, Indiana earlier in the presentation. They will actually be speaking and sharing some of their project with us. So for all of you who need to go, thank you very much. We'll keep the lines open to discuss the rest of these questions with George. But thank you.
Thank you, Corey.
And a quick note to those that are about to leave, we will be sending an email out after this presentation is completed with a form or survey, and please pay attention and watch your email. When you fill out that form, that's how you can receive your PDH credits as well as get access to the video and the documents presented on this presentation. So, but I'll go ahead and hop back into the questions. How about exfiltration, especially in dry weather? Is it significant? This could have significant environmental impact that can be factored in the cost of sewer rehabilitation.
That's a really good question, and to be honest with you, I think that it's not been addressed, or I have seen very little in the literature about exfiltration. Now, interestingly, I was actually involved in a project when I was system engineer in Chattanooga, where EPA came in and did some very detailed measurements on an industrial pipeline, well, an industrial connection that then went into part of our public sewer, and they did monitoring on the public sewer part of the section, and they also had test wells and all kinds of extra work being done to measure the effect of, or what they were mostly interested in was looking at any toxic materials which were getting into the groundwater through exfiltration. I never saw really much come out of that. Now, and there's no way that again, I have a limitation here on as far as this particular study, but just trying to think in overall environmental terms, I'll try to make a comment that if you have a pipe where if you have it's already surrounded by groundwater, of course you're going to have more of a driving head for water to be coming in than be going out. I saw an article years ago, actually, that was printed in 1956, about sewers up in Bowling Green, Kentucky. And if you keep in mind that parts of Kentucky are known to have a significant amount of karst geology, that is a geology that is riddled with caves, is what it boiled down to. There's a lot of limestone, a lot of cracks in the limestone. And they actually had this particular article was bragging about how they didn't have much of a load at the treatment plant because they were able to dispose of it through the leaks in the sewer line and going into the karst geology. I'm not sure that they're very proud of that today, but it was kind of an interesting, let's call it milestone in investigating that kind of a problem. Certainly Tennessee has some of that same kind of karst geology, certainly the limestone geology. I'm not a good geologist, so I'm not going to try to go further on that, but I'm sure some similar situations probably have occurred here.
Okay. We have 3 more questions here. I do encourage any of those that are still on the call that if you do have questions, feel free to keep submitting them. But here I'll go into the next question. In your study, have you seen any connection between the level of I&I in a city system and the predominant material used for pipes or the age of the pipes?
No, and the reason being is, first of all, there's no information that's available in the public records that I have access to that indicate first of all, whatever the predominant pipe material is. But I would also refer back to some of the earlier comments where I mentioned about Fort Worth, looking at the age of their pipes. And again, I'm more saying this as a cautionary point, is that when I first got into this kind of work, in general, I felt like systems with concrete pipes seemed to show more problems. Systems with old clay pipes, if they weren't bedded properly and had failing joints, they seem to be more susceptible to I&I problems. But and I still feel that way to a large degree. But I've also seen a lot of situations where if, say, plastic pipe, certainly water's not going to come through the plastic. But if the plastic pipe is poorly bedded, if you had somebody dropping rocks on it when they were doing the backfill, it can crack the pipe. And also, if the workers aren't belling up the pipes properly and setting the gaskets in the joints, they can be very bad leaks as well. So I'm more trying to just make it as a cautionary note that don't assume automatically that something either is going to be the bad one or that something is going to be the good one. That it's, that's why I strongly encourage people to go out and do the flow monitoring, and then actually see for yourself what Mother Nature's trying to tell you.
Okay, next question is, the O&M cost in many cities is much less than the $1.80 per the 1,000 gallons that you use to justify the payback. So doesn't that mean that it will take much longer for rehabilitation work to pay for itself?
Well, I'll have to admit that I submitted that question, and I did it for a reason, of trying to point out that these are actual comments I've gotten out in the field at times. They say, well, your research is no good. And my response to that is, gee, did you ever think about the relationship between your low O&M costs, meaning you weren't putting any money back into your system, and the fact that you have a horrible I&I problem? So that's the point is, or the moral of the story anyway, is that part of the reason I think that people are having bad I&I problems are not maintaining their system. They're going into this mode of deferred maintenance, and that actually the $1.80 is even on a little bit on the low side of what EPA recommends for maintenance of the system. Now, the $1.80 is a rough approximation of what Nashville spends, and actually Nashville had to raise its cost or raise its rates in order to get to that point, and it's only now that they're actually really addressing, or actually in the past 15 years or so, addressing the major problems that they've had. So the moral of the story is, again, pay me now or pay me later. And it's I think it's better to put a system in rather than have to go through these huge programs to then go back and fix them.
Okay, next question. I see you use 1 year or more of reports to collect this data. Do you recommend collecting 1 year's worth to begin a study of a system?
Yes. You probably could see on those earlier charts where there was variation in the both due to the actual rainfall events, but then there was seasonal variation. And I think in order to get a really complete picture, you need to use a full year's worth of data. But the thing is, it's kind of like, so what? Even to transcribe a full year's worth of data of the rainfall, the daily flows, and the BODs, even if the BODs were collected every day, it took me about an hour to type it in. In the long run, that's all the cost was. It wasn't any extra metering. It wasn't any extra study. I already had the little spreadsheet. So to me, it would probably be nice to put in 2 years data. But since I was trying to do the entire state and I'm just one person, I kind of settled on doing a year at a time.
Okay, next question. Have you seen any correlation between I&I and different geographical/geological settings? For example, for lower or higher I&I and higher mountain elevation settings, or more I&I and lower alluvial settings?
I think that's an excellent question, and it's certainly one that applies here to Tennessee, because we Tennesseans often refer to our state as the 3 states of Tennessee, and that's exactly what happens, is that we have the mountains and the rugged terrain in the east. We have more of the alluvial clay areas, the red clay areas in the west, and the middle Tennessee is kind of a mix of both. But at this point, I haven't been able to, or I want to get all the systems done, and then I'm going to try to do a breakout like that. And so my point is that I think that's a very good question to ask, and I've actually been asked that question before, and I intend to do it. But at this point, and for this particular presentation, I have not had the time or the opportunity to be able to make that breakout. But I will add that I've submitted an abstract for WEFTEC in the fall of 2016, and if that's accepted, I will be covering that kind of topic at that time.
There was a follow-up to that. If you consider multiple years, do you see gradual changes in the INI of the years, or that may have actually been in follow-up to the 1 year question? But go ahead.
Either way, the answer is in certain cases, absolutely yes. And that's one reason why I included that graph for Brentwood. That's a slightly modified graph. I was actually included some different things in there than what the overall study was doing, but it would work out the same way. And the city of Lynchburg, which is a small town that nobody's ever heard of. And the only thing they do, though, a lot of people have heard, is they make Jack Daniel's whiskey there. But that town has done some major work in the past couple years, and I've looked at both the before and after just using the system that I have, and you can see a definite difference. So that's one thing that I would encourage people to look at, is that, and would be one way to get at this question of, well, did we actually achieve anything, is yes, you will be able to see it. If you've been effective in knocking down your INI, you'll be able to see it using these analytical techniques from 1 year to the next.
Okay, that was the last of our questions, George. So,
Super. Well,
George, thank you very much for your time today. Greatly appreciate the insight and sharing everything with us. For everyone on the webinar, as Robert mentioned, we will be sending you the survey to fill out for PDH, as well as if you want a narrative copy. And please provide any feedback of additional topics you do want to hear about. Our next webinar will be March 18th, which we mentioned already. And so thanks everyone for participating. We also do commercial work as well. Want to share an update. Some of you may be aware of it from other blog posts that we've done. But in the commercial realm, we also will stabilize, buildings, footings, anything that begins to settle, and it's partly maybe because of INI that's underneath the surface. 15 years ago, we did this project in Murray, Kentucky for Ryan's Foods, and we actually were joking, calling it the leaning milk silo. And it was a 50,000 gallon milk tank that had settled on one side and was actually leaning. We were able to come in and stabilize the soil underneath, and actually just a few weeks ago, about a month ago, HDR, which is a national reputable firm, did a survey of the tower, and it is not settled anymore in those 15 years. So as you can see, that their survey elevations show that it is the same as it was March 2001. So definitely a great verification of using the chemical grout underneath the soil to stabilize this milk silo. So I want to pass that along as we work with many of you in the commercial space as well. So thought this was a nice letter to share with the team. So anyways, that will wrap up our webinar. Thank you very much, George. And for all of you who attended, please stay in touch with us via social media and our blog posts that we send out as well. So thank you. Have a great weekend, and see you in a few weeks.
Thanks, Corey. Been a pleasure.